All right, hey guys, just a quick little video to talk about some of the homework that you were working on. Right now we're looking at the chapter 4 review. I'm going to go through maybe a little bit of 22 and 23 and then maybe jump around through here. Starting with 22, here we go. Determine whether the statement is true or false. If it's false, give an example for which the statement fails. Part A, if f has a relative maximum at x sub 0, then f of x sub 0 is the largest value that f of x can have. When they say that last little part, it sounds like they're saying it's the absolute maximum, and that's not true. If f has a relative max at x sub 0, it doesn't have to be the absolute max, so that would be false. You can have a maximum, but you can also have a maximum that's bigger than that maximum. So here's an idea right here. So I have two relative maximums. This one's relative. This one's a relative max. If you look at that close little local area, that's a relative max. Look at this little area, that's a relative max. But this one is also the absolute max. If I were to say, hey, look at the entire interval, that's the highest point. Okay, so this right here, let's say this is x naught over here. That's not necessarily the absolute highest, so that would be false. Part B, if the largest value for f on the interval a to b, and it's an open interval, is at x naught, then f has a relative maximum at x naught. Okay, let me read it one more time. If the largest value for f on the interval a to b, open interval, so we're not going to look at endpoints, is at x sub 0, then f has a relative max at x sub 0. I say true. And if you're thinking, wait a minute, well, wouldn't it be an absolute max? Well, fine. Okay. If that's the largest value and it happens to be an absolute max, fine, but it's also a relative max, so this is not a false statement. So true it is. Last one, here we go. 22c, a function f has a relative extremum at each of its critical points. And the answer is false. You can have a critical point where the derivative is 0, but it turns out to not be a relative max or min. Here's an example. F of x equals x cubed, or x to the fifth. I'll do x cubed because it's a little bit faster for us, smaller numbers. So when is that derivative equal to 0? When x is equal to 0. But if we do a wiggle graph, we're going to find out if you go left, you're going to get a positive. If you go right, you're going to get a positive. In other words, because we have an even power here in our derivative, whether you plug in a negative or a positive number, left or right of 0, you're going to get a positive. And that matches with the graph as well. There's a slope of 0 right there, but it's increasing here and increasing there. So not a relative max, not a relative min. Okay, so that was a false. All right, let's continue with number 23. I think that was on the list as well. 23, it says, according to the first derivative test, what conditions ensure that f has a relative maximum at x sub 0 and a relative minimum? Well, first thing is it needs to be continuous. Okay, we need a continuous function to be talking about whether it's a max or a min there. Next, you just want to basically find critical points and find out, so at an x sub 0, if that's a critical point, you're going to go left of that and right of that and figure out if it matches with the maximum idea. In other words, if I go like this, if this is x sub 0 right here, if it's a maximum, it better be positive here and negative there, as in going up and then coming back down. I believe I have it marked in the book. Let me take a look. Yes. Check it out. Here's the first derivative test straight out of the book. And we copied our version down into our notes as well. It may look similar to this. So we need a continuous function at a critical point. The first piece here, part A, has a relative max. So if the first derivative is greater than 0 on an open interval to the left and less than 0 on an open interval extending to the right, then it's a relative max. So basically we need the derivative to change signs in that order, from positive to 0 to negative. And then we'll do the same thing on the reverse. So we want the derivative to go from negative to 0 to positive, and that means it's coming down and then going back up. Right? So graphically, that would look like this. It's coming down and it's going back up. So the first derivative is negative, and then later the first derivative is positive. Okay? So continuous, and then sign change from the derivative, in the derivative from this to that. All right, so that's 23a. 23b, let me see if I can show the book here. According to the second derivative test, what conditions ensure that f has a relative maximum at x sub 0, and then also a relative minimum. Well, second derivative test, let me go ahead and show you what I wrote down. It's got to be twice differentiable, which means you can take a derivative and then take a derivative of that derivative. So you got to be able to take the second derivative first of all, is what we're saying. And then, excuse me, we need the critical point status, right? So we want to have the derivative, the first derivative at x naught to be 0. And then if that's the case, if you're looking for a max, you want the second derivative to be negative, because that means you're talking about concave down at that point. Okay, so if we're looking for a max, we want concave down when you've got a slope of 0 at that point. And then we'll flip that over. Let me sneak one in here. It'll be concave up, so the second derivative will need to be positive if we're looking for a relative minimum. So again, we'll need it to be twice differentiable, so you can take a derivative and take a derivative, so get two derivatives out of it. Then we'll need number 2 to be the same. We need a critical point, so the derivative at x naught is 0. And then the third one, we're going to switch that around. We're going to say the second derivative should be positive, and that will get you a relative minimum. Next up is number 27. We're looking for critical points and use the first derivative test to classify them as relative max, relative min, or neither. So for 27a, we got this weird x to the 1/3 times x minus 7 to the second. So I'm just going to show you this one without cranking it out from scratch. So, and I'll probably send these out or post them somehow, some way tonight. So we got the function. We're going to take the first derivative. So first up, we got a little product rule. So g f prime plus f g prime, right? Next, we're going to try to clean that up. Notice the two piles. Both piles have an x minus 7, so I'm going to factor that out, one of them. And then I'm going to factor out the smaller of the two powers of x. This is where it's a little tricky. We've done this quite a few times, but some more practice. So factor out the smaller of the two powers, which is a negative 2/3. And when you do that, you're going to leave basically 1 power of x minus 7 here, and a 1/3. This is gone all the way. It's totally gone. And then over here, second pile, let's see, the x to the 1/3, when you divide that by x to the negative 2/3, let me show that over here. If I take x to the 1/3, divide by x to the negative 2/3, that's the same as multiplying by x to the 2/3, and then you can add these and get a 3/3, which is just an x to the first. The 2 will remain, the x minus 7 is gone. So we get a nice little scenario in here. It's linear. I love it. All right, so from there, we're going to combine like terms after we distribute. So distribute, get this mess, plus the 2x. We could put those together. This is 6 over 3x, plus 1 over 3x is 7 over 3x, minus 7/3. So not loving the fractions, but it is what it is. We can deal. So now we've got an x minus 7 over here. We got that stuff over there that we can clean up. We can bring those together. That'll get me a 7/3 x. And then let's see here, the x to the negative 2/3, I just bumped it down to the bottom, made it a positive power. Okay, from there, if you notice, you don't have to do this, but if you notice it, you can factor out a 7/3 here, and that's going to leave you a nice little x minus 1. So if you see that, great. If not, that's fine. Set this equal to 0, set that equal to 0, set that equal to 0. Get all your critical points. So we got a critical point when x equals 7, of course, when x equals 1. And then down here, 0 to the 2/3 would get you a 0 on the bottom, so the derivative's undefined there. So that's still a critical point. We get stationary points from these two guys right here. 7 and 1 are stationary points because they make the first derivative 0. And then all three of them are critical points. It did say to figure out if they're relative max, mins, and neither. So we're going to make a little sign chart over here with our three critical points, 0, 1, and 7. And now I'm plugging into one of these forms of the derivative. I did this last year. I think I plugged it into here. I like the factored form. That usually is pretty easy. So here goes. Plug in negative 1. We're going to get positive, negative, negative, positive, because you got an even power right there. So you'll square that negative 1, make it positive. Cube root will still be positive. So that's all going to be positive, because negative times negative is a positive. Good. Next, we go in here, in between 0 and 1. Like a 1/2. That'll be a negative, that'll be a negative, still positive, still positive. So all positive again. Plugging in something in here, 2, 3, 4, 5, 6, somewhere in there. Oops, lights are out. And lights are on, here we go. So plug in like, I don't know, 3 or 4. How about 4? That'll be negative. This will be positive. That'll be positive, positive. So that'll all work out to a negative. And last but not least, plug in 8 million, or 8 is fine. Positive, positive, positive. It's all positive. All right, so there we go. We got some increasing, increasing, decreasing, increasing. I see a change in sign right here. So that makes 1 a relative max. Over here we have a change in sign from decreasing to increasing, so that's a relative min. And there's not a change in sign. There's no change in sign, I repeat. No change in sign at 0. So we have not a max, not a min at x equals 0. All right, I'm going to go ahead and stop this video here, and if I have some time, I'll try to put together another one. Thanks.